So I'm right now going to exercise this column involving in the time domain sine and cosine signal, and involving the multiplication of exponent potential with the sine and cosine. So from there we know the cosine bt is the Laplace transform is as, and here look at this carefully. For cosine, whatever the frequency, that is s squared plus frequency squared, that is numerators. Doesn't matter if it's sine or cosine. Okay, that's a way to memorize the things. So here is the frequency. So here is s squared plus frequency squared. Okay, so that is for cosine, and numerator is s. For sine, that is s squared, the same numerators, s squared plus frequency squared. Okay, and numerator here is b. So here we can do the exercise here. So for example, I want to calculate the inverse Laplace transform of this. If you compare to the second one, that should be equal to sine t. Right? Another example, say 1 s squared plus 4. What is this? Sine 2t. And what is its coefficient? 1 or 1/2. That's the tricky part, and most of the time students make a minor mistake here. That should be 1/2. If you look at this carefully, so basically this one, 1 s squared plus 4, and that one equal to 2 times s squared plus 2 squared and 1/2, right? I want to make up the form that appears exactly like this. Good. So you have to make up the form that make up your numbers exactly as this one. Then you can apply the table. Okay. So to make up that one, basically the second portion, the plus inverse, is sine 2t. So in this way, we have half appeared at the front. Okay. So basically this one is cosine t, and the plus inverse as squared. Thank you. So this one is simply cosine 2t. Good? Okay. So this is very straightforward. And now I want to exercise the following two terms here. So here if we have exponent, this corresponding is this. If in the time domain, for any harmonic functions, if it multiplies with any exponent, and that categorized by a, okay? So corresponding Fourier series transform, and look at this carefully. The first one, you look up what is the patterns for cosine bt, which is this one, okay? You write it up, this one. S squared plus b squared. So this is the patterns corresponding to without exponent form, okay? And right now this multiply with exponent at. So in this way, you base upon the platform, you do a replacement. You replace s by s plus a. S plus a or minus a, sorry, minus a. So basically this one is equal to s minus a, s minus a squared plus b squared. So this is a corresponding Laplace transform of this composite time function. Okay? So this one is very easy, can be easily done by you simply first look at the patterns of without the exponent term, and then from that term onward you do the replacement like this, and that's it. In a similar way, E AT times sine BT, that is the same. For BT is B S squared plus B squared, and you do the replacement S by S minus A. So basically this one is equal to B. Okay. So here we can do a little bit of exercise. So we do this one here. So Laplace transform S squared plus 2s plus 1 plus 2. Okay, so for this one, that can be equal to Laplace inverse. Let me operate the numerator denominator first. I want to have something squared, this one inside have s contained, and with some other constant. Okay, so if you know s squared plus 2s plus 2, I want to have this one be expressed in terms of the complete square term and plus some kind of residual constant. This one you can see that one can be easily done by this s squared plus 2s plus 1 plus 1. This one is s plus 1 squared. Okay, so let me copy that one here. Okay, so right now I'm kind of doing something such that I can utilize the table. That is the goal. Okay, don't feel kind of weird why I do so, but with this in mind, then we want to calculate the Laplace inverse. And you know that from here, this is the square terms of the numerators and the denominators. So once you look up the Laplace transform table, you simply look for the denominator that has a square term. Very likely this would appear, but it's not exactly the one. We drop it. This one, well, very close, but not exactly, because here we have the kind of the additional constant term here. So the only thing allow us is looking into this column, and very likely the two information here. Okay, so we're fitting carefully. So right now look at this one, and that is very, very close to the simple one. It's something like this. So you can compare with this example before. So here you can see, if I can, in your thinking process, and not to make a mistake, and right now I'm kind of let you know the exact way, the easiest way not to make any mistake. For this one, if you can do a replacement, if you replace s plus 1 by s, okay, so in this way, you can see, we do the replacement. Basically, this one is equal to Laplace inverse. Equivalent is this one, s squared plus 1, and then you do the replacement s plus 1, something like this one, right? Okay, they are equivalent. Okay, so right now you compare to our template here. This form basically give us this is sine t. This form give us is the inverse is sine t, right? But here we do the replacement. So basically you plug into the replacement. When we do the replacement, s equal to minus s minus a, corresponding is at. So here we corresponding is to multiply with e minus t here. Be good? Okay? Good? Okay, try to get used to it. So probably today we stop here, and next time coming back, I will continue the exercise of this form. Okay.